Talking about Chapter 8, which is going to be dealing with enzyme kinetics for the most part. A couple things to note before we start talking about that. Just as a reminder, we do have an exam. It is next week. I know I've said that I'm going to remind you guys by sending out an announcement on Blackboard, but I've yet to do that. But most of you already know that there is no exam today. It is next week instead. I do have a practice exam online. It does not have a key at this point in time. I'm going to try to rectify that by this afternoon. So hopefully I will put up a key again by this afternoon. There are a couple questions on the practice exam that we may not necessarily get to, and I will try to denote that whenever I go over the key. So certain questions that I don't think we're going to necessarily cover or I have not covered, I will denote when I post the key for that. Couple other things. So I've also posted a bunch of homework. Okay, so Chapter 6, Chapter 7, as well as Chapter 8. All of those are posted on Mastering Chemistry. Chapter 6 and Chapter 7 have a due date of this weekend, I think. I'm pretty sure. Chapter 8 has a due date, I think, of next weekend. Okay, so I would just start looking at those now. With respect to 6 and 7, there are pretty much a lot of fairly just easy, knowledgeable, like reading assignment-based questions, but there are a couple of them that are a little bit more difficult. So about 3 to 4 of those in Chapter 6 and 7 are a little bit more conceptually challenging. So you may want to come see me before the weekend so that you don't get stuck not knowing what to do before the due date for the assignment. All right, does anyone have any questions? Yes. No, so if you look at the practice exam, it's pretty much exactly like I presented on the practice exam. The first sheet, I give you 10 amino acids. I either give you the 3-letter, the 1-letter, or the actual name conventions, and I ask you to draw them. Okay, so there's 10 of them. I give you 10 different ones. That's pretty much exactly how it's going to be. Okay, so the way that is going to go, I didn't really want to talk about it today, but the way that's going to go is you guys are going to get the amino acid quiz first, right? So I'm going to hand out a sheet with the amino acids. You guys are going to finish that. You're going to turn it in, and that's when I'm going to give you the multiple choice portion. Okay, so it's like 2 different exams in one, which may be very challenging, so I apologize with respect to that. I will try to keep that in mind as I am preparing for the exam. Okay, so fingers crossed it goes well for everyone. All right, so any other questions? Yes, no, okay, good. All right, so we're going to start talking about Chapter 8, which I've kind of been avoiding because it gets really dry and monotonous, as if this class has not already been dry and monotonous. But today we're going to start talking about enzyme kinetics, okay? So before we can start talking about enzyme kinetics, I'm going to remind you guys of a couple of features with respect to chemical kinetics that you should already be aware of, but I want to make sure that we're on the same page. Okay, so thus far, if you wanted to kind of consider this unit with respect to biochemistry, we've been talking a lot about proteins, right? So we started talking about amino acids, we started talking about secondary, tertiary structures, and then last chapter we built that up into explaining the actual properties of myoglobin as well as hemoglobin, right? How proteins could essentially accomplish their various functions. So one of the big roles of proteins in biology is in the form of enzymes. And so that's why it gets its own little chapter and why we're so interested in enzymes. Okay, so what is an enzyme? An enzyme, number one, mainly is a protein, right? So it's a protein that is folded into a nice little tertiary or quaternary structure. But the role of enzymes in biology is to act as catalysts, right? So what is a catalyst? Right, so it's a chemical species, number one, that speeds up the rate of a chemical reaction, but most importantly, it is something that is not consumed in the overall reaction. Okay, so an enzyme will increase the rate of the reaction, it will itself not be consumed. Okay, so why do we need enzymes? Why do we need catalysts in biology at all? So, garble, yes, so some things, right? So number one, all biological reactions are thermodynamically favorable. Okay, so that's one thing that's important to note. All chemical reactions that take place in the body are thermodynamically favorable. The problem is that they are kinetically extremely inert, so very, very, very slow. So if we were trying to sustain life, if we were just waiting on these reactions to occur, they would not be capable of doing that because, again, they are all so very, very, very slow. So that is the role of enzymes in biology. It's to speed up these processes so that life is actually capable of occurring, okay? All right, so a nice little example of this idea behind things being thermodynamically favorable but very kinetically slow is given in this example of hydrogen peroxide, right? So hydrogen peroxide spontaneously decomposes into water and oxygen, right? But if you put hydrogen peroxide on your bathroom shelf, do you see it spontaneously decompose within the course of your lifetime? No, right? So again, even though this reaction is thermodynamically favorable, it's going to occur, it's trying to go to equilibrium, it is very, very, very slow. And so because of that, we don't actually see this reaction occur within the course of your own lifetime. Now, this reaction in the presence of this enzyme catalase, which increases the rate of this reaction very, very, very much, essentially, again, catalase is the reason why we actually need enzymes, okay? So again, we have reactions, they're thermodynamically thermodynamically favorable, but they need an enzyme to actually make them go in the time frame of our actual life, okay? So what I really want to point out here is, number one, to be a catalyst, right, to be an enzyme, it must remain unchanged over the course of a reaction, okay? So catalysts have to remain unchanged. If we change the catalyst, then it's no longer a catalyst. Number two, enzymes are not going to make thermodynamically unfavorable reactions favorable, okay? All they're going to do is essentially speed up the rate at which we get to equilibrium in a thermodynamically favorable reaction, okay? So catalysts cannot be consumed. Number two, we cannot make thermodynamically unfavorable things happen. All they're going to do is just speed up the rate to which we get to equilibrium, okay? Okay, so roles of enzymes in biology. Speed up the rates so that we can actually make all of these processes occur. All right, so there are a lot of different types of enzymes, right? And so with respect to, like, let's say organic chemistry, right? In organic chemistry, you guys spend a lot of time learning how to name things, right? Why is that? Why do we have to spend so much time learning how to specifically name an organic compound? So mainly the idea is, if I'm dealing with something and I know what kind of chemical I'm dealing with, it's so that if I give it to you, you're dealing and know exactly what type of compound that you're dealing with, okay? So we have all of these various systematic naming schemes with respect to chemistry to essentially make sure that everyone is on the same page with respect to whatever type of molecule we're dealing with or whatever type of enzyme we're dealing with. We're not going to necessarily do the same thing with respect to enzymes. So there are a bunch of different types of enzymes. I'm not going to go over how we actually go about naming them because a lot of their more common names don't have any type of rhyme or reason as to why they're named that way. But what I am going to say is that all enzymes are essentially classed into 3 or 6 different types of classes, depending on the reaction that they catalyze, okay? So these 6 different types of classes are given in this little table here. All right, so again, all enzymes can kind of be grouped within one of these classes, and again, this depends on the overall reaction that they catalyze. So the first class of enzymes that we deal with is something called oxidoreductases, okay? And so for oxidoreductases, these enzymes involve the transfer of an electron in the overall reaction. Transfer. Makes sense, right? So a lot of times with these oxidoreductases, they will involve some sort of redox active cofactor. This could be NAD, NADP. It could also be some sort of metal ion or metal cluster. Second one we call transferases. So transferases deal with the actual transfer of functional groups, right? So for example, here we have this hexokinase. So hexokinase transfers a phosphate to glucose to form glucose 6-phosphate. This is the transfer of actual functional groups. Transfer of functional groups. So So the third class are called hydrolases. So these hydrolyze bonds. They break bonds, essentially. So all of our little proteases are hydrolases because, again, they break the peptide bonds. They add water to the peptide bond, breaking it, and that's the overall job of a hydrolase, breaking bonds. So the fourth class is called lyases. So lyases deal with lysis reactions. This in general is going to be kind of like an elimination reaction. And the formation, we're going to see the formation of pi bonds in these lysis type reactions. Fifth is isomerases. So what do you think isomerases do? Isomerize things. So this can be both constitutional isomers, forming it into a different other isomer, or this could also be the isomerization of stereoisomers. And then the last one, ligases, fairly easy. What do you think they do? They ligate things together, right? So they're going to join two separate things. With respect to this, this usually involves the hydrolysis of ATP. So ligases usually have to utilize ATP to make bonds form. Okay, so again, those are the 6 various classes of enzymes, right? And so there's this large database. If you go in, yes? What, sorry? Number 4. So lyases essentially perform lysis reactions. This is kind of like an elimination reaction. So usually catalyze the formation of pi bonds. Okay, so again, there are these large databases that categorize all of the enzymes that we have in nature in these 6 different types of classes. Okay, so I just want to let you guys aware of those classes. All right, so now we're going to talk about chemical kinetics. We're going to go back, we're going to talk about just basic chemical kinetics, because enzyme kinetics is just another branch of chemical kinetics. So to make sure that we're all on the same page, we're going to start with these very simple chemical reactions, okay? All right, so let's imagine that we have a chemical reaction where we have A going to make product, okay? So with respect to this reaction can occur as a single step, right? So A just going to product, or this can occur as a series of separate steps, right? So for example, we could propose that in this reaction, we have A first going to make I2, and then I2, and a second reaction forming, or I1 forming I2, and then in the third reaction, I2 is going to form product, right? So in these separate steps, this is what we're going to call a mechanism, okay? So this again is a series of different steps that essentially attempt to explain our overall chemical reaction. So one thing with respect to a mechanism that has to be met is the fact that all of these separate steps that we have proposed for our chemical mechanism, what do they have to do if this is going to be valid for our overall chemical reaction? They all have to sum to the overall chemical reaction, right? So if we have a mechanism and it's going to be valid, it must sum to the reaction that we are trying to explain the actual chemical process for. So when we do this, we'll find that these I's cancel, and we are left with A going to P. Okay, so in this chemical mechanism, what do the I's represent? What do we call those? Things that are made in an early step and then used in a later step. What are those called? Intermediate species, right? So I1, I2, these guys are both intermediates. So there's a problem with intermediates, right? Can we necessarily know that they exist? No. The only thing that we can really ever measure for the most part, for most chemical reactions, is reactant and product. Okay, so intermediates are things that are fleeting and may or may not exist. Okay. Also, with respect to this mechanism, what are these individual steps called? So individual steps in a chemical mechanism are essentially our attempt to explain at the molecular level what's actually occurring, right? So in our first step, we have A, it is reacting and forming I2. So what is this first step called? All of them together, they're all what we call elementary reactions, right? So each step in a chemical mechanism is what we call an elementary step or an elementary reaction. And what is really great about an elementary step? So we'll get to that in a second. So we'll talk about what's great about elementary steps in a second, okay? All right, so we've got intermediates. Intermediates are things that we can't necessarily isolate. They are made and then immediately consumed. Again, though, the mechanism itself is our attempt to explain at the molecular level how this overall reaction is occurring, and it is consistent of separate elementary steps, okay? Okay, so let's talk a little bit more about this nice little reaction. So also, a second thing to note, this single-headed arrow, what am I trying to indicate by a single-headed arrow? So this reaction right now we're assuming is irreversible. Okay? All right, so next. So how do we measure reaction rates? So let's say that, again, we have this little reaction, A going to P, and I make my little drawing out here because I'm preparing for how I'm going to explain this. What is a rate? What is it usually defined as? Right, so something's happening per unit time, usually. So in respect to chemical reactions, how are we normally going to measure rates of reactions? Concentration changes per unit time. Okay, so our rates are usually defined in terms of molarity per second or a change in molarity per unit time, okay? So if I have this reaction, I have P, or I have A, and I have P, and I want to measure the rate of the reaction. Let's assume that initially I start with only A, and we'll say that concentration is over on our little y-axis, and I have no P, okay? On the x-axis, we're going to be measuring time, and we can just imagine that this is in seconds, okay? All right, so if we start this reaction, what's going to happen to the concentration of A? It's going to decrease, right? So we're going to have we're going to have A decreasing. What's going to happen to the concentration of P, our product? It's going to increase, right? So as this reaction continues to occur, what's going to happen to the overall rate of the reaction? It's going to start to slow down, right? So as we're losing A, we have less of it, so less of it's going to be able to react. At the same time, as we're gaining P, we have more of it. It's going to, again, start to slow down, okay? At some point in time, we are going to reach equilibrium. All right, so now, if I want to measure the rate of this reaction, and I want to measure it in terms of A, how would I do that? Say I had a state up here, which we'll call the initial state, and I had a state down here, which we call the final state. How would I measure the overall rate in terms of A, the species A? So I would measure the change in concentration of A over change in time, right? That's something that we can measure. What's the problem with the overall sign with respect to this delta A over delta T? So if we have a final state that is less than the initial state, and we're taking final minus initial, what's going to be the sign of this guy? It's going to be negative, right? And so because of that, we don't want to deal with negatives, so we usually put a negative in front so we get a positive overall rate. What about P? What if I wanted to measure the rate in terms of P as opposed to A? So again, we'd have some final time here, some initial time here. We can measure the rate in terms of P as change in concentration of P over change in time, but do I have to worry about the sign now? No, because the rate's going to be positive. As long as this is 1-to-1, are these rates going to be the same regardless of who I measure? Yes, okay? So that's how we essentially will go about measuring these rates of reactions. So the rate of the reaction, for whatever reason in biochemistry, gets replaced to the word velocity. Okay, so velocity takes over for rate. I don't know why they do that, but we're just going to start using it now because we have to use it later. Okay, so I'm going to represent rate as a V for velocity. Okay, and again, we can measure the rate of the reaction as the negative change in A over change in time, or we can measure the rate of the reaction as the change in P over change in time. Another way to write this, and getting rid of this delta notation, is to write this as derivatives. So this could be negative dA over dt and dP over dt. And that's what we're going to move forward with, is writing these guys as derivatives. Okay, so that's how we measure rate, right? We've also already alluded to one specific thing. How do rates and concentrations relate to one another? How are they related? So concentration is one really important parameter with respect to affecting the rate of the reaction. So are they inversely proportional to one another, or are they directly proportional to one another? Directly proportional, right? So the rate of the reaction, or the velocity of the reaction, is directly proportional to the concentration of reactant species, right? Is this always a direct proportionality? It depends, right? So this could be a direct proportionality if this little exponent was 1. It could also be proportional to a squared if this exponent is 2. What is this exponent called with respect to kinetics? Orders, right? So N here is referred to as order with respect to whatever chemical reaction we're referring to. Okay, so N, what values can N be? So N could be 0, 1, 2, even up to 3, though it's fairly rare. Another little thing to note, if I want to replace this proportionality with an equal sign, I can do that, but what else do I need to include? A constant, right? So as long as I include a constant, I am good. What is this little k called? What is this little constant called? This is called our rate constant, right? And how does it relate to the overall rate of the reaction? So the larger k is, what can we say about the speed of the reaction, the velocity of the reaction? The faster the reaction, okay? Okay, so k is going to be this little constant of proportionality. Again, what is this called? This is what I get at when I was talking about the elementary step. This is called the rate law, right? So the relationship between concentration and rate of reaction is what we refer to as the rate law. Again, for most reactions that we're going to be dealing with, this N is going to be 1, right? So these guys are going to be just directly proportional to one another. How do we determine rate laws? For an overall chemical reaction, you determine rate laws by going in and experimentally determining how the rate of the reaction varies with concentration of reacting species, okay? So rate laws like this have to be determined experimentally. But again, getting back to those elementary steps in our mechanism, what's great about an elementary step? You can essentially look at the stoichiometry of the elementary step and be able to predict the rate law directly from that, okay? So if this was an elementary step and I wanted to predict the rate law directly from this, I could, because there is a 1 in front of the A, okay? So in elementary steps, the stoichiometry essentially tells you the order of the various reactants. So the rate law for this elementary step would be rate is equal to Ka to the 1. Okay, so in elementary steps, you can directly infer what the order of the reaction is just by looking at the stoichiometry of the step, which is what's so great about elementary steps. Experimentally, though, if you wanted to know the overall rate law for the chemical reaction, you would have to go in and determine it experimentally, okay? All right, so anytime that we have a reaction where we have only one reactant species, right, so everything is going to be first order, then we call those unimolecular reactions, pardon me. So unimolecular reactions just depend on one specific species, okay? Okay, so that's some basics. We have rate law. We also have how we're actually going to measure reaction rate. So we're going to take these two things, right? We have rate in terms of actually measuring parameters, and we also have rate in terms of our concentration of reacting species, and we're going to put those two together because, again, the rates are going to be equal to one another. Okay, so when we do that in a unimolecular irreversible reaction, we are left with this guy, okay? So this is what we call a rate law, the derivative form of the rate law. We can take this guy, we can separate variables, and we can integrate, and we are left with what we call the integrated form of the rate law. So what is this going to tell us with respect to, let's say again, we have only one reacting species, A, going to make products. What does the integrated rate law tell us? How the concentration of this guy varies as what? A function of time, right? So a couple of things that we need to know with respect to these integrated rate laws. This, again, is going to be concentration at whatever time we're looking at. What is K here? This is just our rate constant. And then what do you think this A to the 0 subscript means? Initial concentration, okay? So if you know the initial concentration, you know what time you're looking at, you know the rate constant of the reaction, you could determine the concentration of your reacting species via the integrated rate law, okay? One other thing to note that we're going to define is something called the half-life, okay? So half-life is defined as the time it takes for the concentration to get to 1/2 the initial concentration, okay? I'm going to take this guy and I'm going to write this in a different way. So I'm going to write this as AT over A naught is equal to minus KT. And then I'm going to substitute the fact that at half-life, concentration of A is 1/2 the initial value, okay? And I'm going to substitute that in to my little integrated rate law. I'm going to be left with ln of 1/2 of A naught over A naught is equal to minus KT. What cancels here? The A naughts cancel, and we are left with ln of 1/2 is equal to minus KT. This is just a number. It's minus 0.693 is equal to minus KT. And so when we solve for T, we'll find that the half-life is equal to 0.693 over K. So this is for a first order reaction. So that is the half-life expression again for a first order specific reaction. Okay, so first order, also irreversible. What happens if we make this reaction reversible? So let's imagine that we do have a reversible reaction, okay? So in this reversible reaction, we have a reaction that has a rate constant forward, and we also have a reaction that has a rate constant in the reverse, okay? So how would I write, again, if this is an elementary step, how would I write the rate law for the forward reaction? So we have only one reacting species, right? It has a 1 in front of it, so it's first order, because again, this is an elementary step. We have a rate constant associated with it. So the rate law for the forward reaction would just be rate is equal to K times A raised to the first power, right? How would I write the rate law for the reverse reaction? Again, the reverse reaction has its own little rate constant associated with it. Who is the reactant in the reverse reaction? B. So the rate of the reverse reaction can be written like this, where rate is equal to the inverse K, or K minus 1 times B, okay? Now, this is a problem if it's reversible, right? So beforehand, we were assuming that the rate of our reaction, or the rate of change of concentration of A, was strictly due to A disappearing, right? But as A disappears, what's going to start happening? B is going to appear, but what's going to happen with respect to B? It's going to start making A again, okay? So now, the rate of these reactions have to account for the fact that we're utilizing A in the forward reaction, but now we're starting to make A in the reverse reaction, okay? So this is going to be using A and then making A. So the overall rate of the reaction would have to account for the two of these if we wanted to measure it via following the concentration of A. Big thing to note, at equilibrium, what happens to these rates? We reach equilibrium, what happens to them? Rate of the forward reaction equals the rate of the reverse reaction, right? So if we substitute this guy in, we essentially will get a relationship where the concentration of B over the concentration of A is equal to K1 over K minus 1, right? So at equilibrium, we have defined this ratio of concentrations as our equilibrium constant, but what can we also define as the equilibrium constant? The ratio of the rate constants, okay? So ratio of the rate constants is the exact same ratio that we get from the ratio of the actual concentrations, okay? So at equilibrium, we have these concentrations, they're no longer changing. We also have these rate constants that have stopped changing as well. Okay, so equilibrium is an important point to note here. And again, we can get these ratio of rate constants from that. All right, so these were all unimolecular reactions, right? We had one reacting species. Now what happens when we have a reaction where we have two reacting species, okay? So something that's a bimolecular reaction. Okay, so again, if this is an elementary reaction, what can we say about the orders with respect to A and this A plus B going to make P? So there's a 1 in front of the A, there is a 1 in front of the B, right? If this is an elementary step, then this is first order with respect to A. What is the order with respect to B? It's also first order, okay? And so a nice example of this would be given by myoglobin binding oxygen, right? You have two interacting species, they have to come together, and so one has to bind with one, and that's why we get this first order for both of the two reactants, okay? One big thing that we should note that we don't have to deal with unimolecular reactions is what happens when we actually do have two things in a bimolecular reaction, right? To react, what has to happen to them? Can they be over here and over here? No. So a big thing that has to happen with respect to these guys is they have to collide, okay? And that's a big assumption that we make with respect to these types of bimolecular reactions where you have two different things that are dependent on the rate. Okay, so for this type of reaction, we can measure the rate or the velocity for the reaction by following the decrease in myoglobin as a function of time. We could also follow it by measuring the decrease in oxygen as a function of time. But the rate law for this overall reaction is given by KMB O2, because again, these are both first order reactions. Okay, so bimolecular would tend to see, so those are two things colliding at once. What about a termolecular reaction? That would require three things to find each other collide at once. How frequent do you think that's going to happen? Pretty rare for the most part. So anytime that we have larger type reactions, right? So we have multiple things that have to collide. How do we explain their various reactions if we can't have more than two things collide at the same time? So if we had, let's say, 4 reactants going to make products, how do you think we would go about trying to explain how that reaction actually occurs if it's very improbable that more than two things are going to collide at once? So a mechanism, right? So anytime we have multiple things above two things that have to collide at once, this is when we invoke our mechanism to explain what actually happens in the chemical reaction. So we'll explain that as a series of separate steps where, again, one thing or two things collide at the same time, okay? And again, what's important, what's great about a mechanism with respect to elementary steps, you can predict the rate law directly from the elementary steps, okay? Another important thing about a mechanism, what step is essentially referring to the overall rate of the reaction, right? So let's say I had a mechanism, we'll just go back to this guy. So I've got this mechanism that's going to explain my overall reaction, right? One of these is going to be slower than the other. What do we call that? Rate determining step, right? So one of these is going to be slower than all of the others, so everything else is going to be fast with respect to that. We call that the rate determining step, and the most important thing to take away with that with respect to the rate determining step is that this step is going to determine the overall rate of the entire reaction. So when we're watching a reaction, what we're really watching is the rate determining step in the mechanism. Okay, so rate determining step determines the rate of the overall reaction. And so it's essentially reporting on its own little elementary step, its own little elementary step rate law. Okay, all right. All right, so let's take a problem. Let's try a problem. So I have a hypothetical elementary reaction. I give you the rate constant, and I want to know what is the velocity at 10 millimolar concentration of A. No. Okay, so go and get your answers in. All right, so what was the answer to this? I gave you multiple choice. So it was like B, right? So first off, how do I know what the order of this reaction is? How do I know what the order is with respect to A? They tell you specifically this is an elementary reaction, it's an elementary step, and the stoichiometry for A is 1, right? So I know this is a unimolecular first order reaction with respect to A. How would I measure, or how would I calculate the velocity? If I know the rate constant and I know the concentration. All I have to do is plug these guys in, right? So velocity is equal to rate constant times 10 to the minus 6 inverse seconds. And then the concentration of A is in 10 millimolar, but in my answers I gave you guys all velocities in molar per second, right? What did I do? That's weird. Let me save. Okay, so I plug in the rate constant, I plug in my concentration in molarity, right? So 10 millimolar is 0.010 molar. And I calculate this out, I end up with 5 times 10 to the minus 8 molar per second. You guys can see that at this point in time. Okay, so this is super simple, but there is a question just like this on the practice exam. Just note that. All right, so the second one, I want you to utilize the half-life expression, but there is a change in this. I want you to calculate the half-life in minutes, not years.
Are we getting points for this?
No, you're not getting points for this.
Because I got it right. I got 3.2.
Yeah, you got it right, yeah.
But I just won 6x.
Yeah, don't worry. Yeah. No, you don't need to write the units. Okay, so go get your answer in. I feel like most of your look pretty good. Okay, so what is the answer for this? So we get about 3.21 minutes. What I should note is that this half-life expression that I derived was specifically for first-order reactions, right? So again, how do I know that this is a first-order reaction? Yeah, there's one in front. I should have mentioned it's probably an elementary reaction as well, but we'll just assume that, okay? So determine the half-life. If we have the rate constant, we just take 0.693 divided by the rate constant. What are the units of the rate constant? So this is inverse seconds. So when we get this ratio, it's going to end up in seconds. So 0.693 divided by 3.6 e to the minus 3 gives me 192.5 seconds. And so then to convert that to minutes, I would just divide by 60, 3.21 minutes. Okay, all right. So, unfortunately, I will not give you these types of equations on the exam, okay? I probably won't ask about the integrated rate law, but maybe you should know the half-life expression for a first-order reaction. It's fairly simple, and if you think about it, you can derive it on your own. Yes? No. Probably not, most likely. Unless if I did, I would give you the integrated rate law for that reaction. Okay, so let's continue on with this fun stuff that we're doing. So we just talked about how the concentration of reactants affects the reaction rate, right? That is detailed in the rate law. What other various factors affect the overall velocity or rate of a reaction? So another factor that affects the rate of a reaction, temperature, right? So temp is one. Are there other things? Pressure is kind of like concentration. pH is probably going to be something like concentration. If you just go back to the idea behind collision theory, right? So we need molecules to collide to actually react. What's also going to affect the reaction rate? Concentration, temperature, but also probably just number of collisions, right? Number of collisions per minute. So number of collisions, which has to do with concentration, yes. Also, what about orientation, right? So orientation is a very specific little parameter that overall affects the reaction rate, okay? All right, so if we go back to just our general rate law, so rate is equal to K A first order, first power. Where does temperature come in to affect this rate law? So temperature, as is written right now, is not in our overall rate law, right? But temperature affects what part of this rate law? K, right? So the rate constant is where this effect of temperature actually comes into play. And we're going to talk about how that actually can be quantified, okay? So with respect to how we envision these overall reactions occurring, we invoke this idea behind transition state theory. Okay, so you guys are very familiar, I'm sure, at this point in time with what transition state theory deals with. Okay, so if we were to just imagine that we had reactants and we had products and everything just depended on thermodynamics, right, then everything that was at a higher energy state as a reactant would just immediately fall to products and everything would just occur as is written, right? We know that doesn't occur, right? We know that some things are very, very, very slow. And the reason why some things are very slow is because they have to go through this high energy intermediate state, which is what we call the transition state. And we denote by this little, I don't even know what this is. It's like a cross, two crosses on a stick or something like that, okay? All right, so most reactions to actually go from their reactants to their products have to go through this high energy intermediate, which is what we call the transition state, okay? Now, how can we imagine this going through the transition state? So the book likes to invoke this idea going between the boat conformation of a cycloalkane and the chair conformation of a cycloalkane, okay? Between the boat and the chair, who is more stable? The chair, right? But how do you get from the boat to the chair? If you actually move with the little molecular models and you actually move from the boat to the chair, you have to go through this very high energy intermediate state, which is the half chair, okay? So this was what we would imagine for this reaction as the transition state. If you looked at the various conformations in this half chair, you would see it's super high in energy because of what? What determines these energies in these cycloalkane structures? Right, or the eclipsing conformations in the overall cycloalkane structures. So in the chair state, all of our carbons are nice and staggered, but when they move through these high energy states, they're going through these eclipsed high energy conformations, okay? Okay, so this is our transition state. This energy difference between the reactants and this transition state, which is a fleeting intermediate, is what we call the activation energy. We denote that as a delta G naught with our little double cross, or what we've usually called this and denoted it as E to the A, so activation energy, okay? Okay, so again, this is the energy that these reactants have to essentially have to overcome this barrier and fall to products, okay? So how could we, or first off, let's just say we have a reaction, it naturally occurs, right? Where do they get this energy to get over this activation barrier? If we have reactants, where do they actually get this energy from to begin with? Temperature, right? So the first thing is, number one, thermal energy is where most molecules actually get this energy to overcome the activation barrier. Okay, so thermal energy is our number one source of energy for molecules to overcome this barrier. Now, if we think in terms of biological reactions, what's the problem with depending on thermal energy to increase the rate of a reaction? Right, so with respect to biology, we kind of keep within this nice, tight, regulated temperature range, right? We can't increase the temperature of our various biological molecules to overcome these activation barriers because, again, most things would denature. So what is another way that we could have more molecules have enough energy to overcome this barrier? What could we do to the barrier itself? We could lower it, right? So we could lower the barrier or lower the activation energy in some way, then the majority of molecules that we already have at their normal thermal energy would have enough energy to overcome that barrier and fall to products, okay? So which one do you think enzymes do? Do you think they increase the thermal energy by increasing the temperature of the system, or do you think they do stuff to lower the activation energy so that most molecules can overcome that barrier? Lower the activation energy, okay? So again, enzymes are going to have a variety of different ways in which they do this, and I'm going to talk about that on Thursday, okay? So how do enzymes actually lower activation energy? This is what I'm going to go over on Thursday. Okay, so we need to lower our activation energy. That's great. That's what catalysts do. That's what enzymes are going to do. All right, so in a catalyzed reaction versus a non-catalyzed reaction, we can actually calculate how much rate enhancement we see in a catalyzed reaction. Okay, so the actual equation that relates rate constant to temperature is given by the Arrhenius equation, which is over here. And I just want to note that there needs to be a negative in front of this. I missed this when I made the actual thing. Okay, so rate constant and its dependence on temperature is given by the Arrhenius equation, right? So again, delta G here is our activation energy. It's delta G naught, or whatever this thing is. I don't even know what to call it. This also, again, depends on temperature as well as the gas constant R. Okay, so this is temperature in Kelvin, and R is our gas constant. What is A? So A, we consider something called the frequency factor, right? This is essentially a measure of the number of times molecules try to actually overcome this barrier. For most biological reactions, this ends up being a very large number, about 6.4 times 10 to the 12th, and we model it on the vibrational frequencies and bonds. So we're going to ignore A for the most part. Okay, so again, rate constant, this is our relationship to rate constant in activation energy. So if we have a catalyzed reaction, and we have it comparatively to an uncatalyzed reaction, we can calculate something called the rate enhancement, which is essentially the enhancement in rate of reaction in the catalyzed versus the uncatalyzed reaction. To do that, what we can do is we can compare the rate constants for the catalyzed reaction and the non-catalyzed reaction. And if we plug in our little Arrhenius equation for both of these, this reduces down to this little thing, okay? So now, if we imagine that this A is similar for the catalyzed and uncatalyzed reaction, then this rate enhancement depends entirely on what we're going to call delta G, right? Which is the difference in delta G, or activation energy, for the non-catalyzed reaction versus the catalyzed reaction, okay? So again, what we're looking at is essentially this difference in activation energy, okay? Now, to see rate enhancements on the order of 10 to the 13th, so 10 to the 13th times faster in the catalyzed reaction versus the uncatalyzed reaction, what we will find for these delta G's is that these will be on the order of about 30 to 90 kilojoules per mole difference, right? So with respect to energies and with respect to various non-covalent interactions that we find, how much change in this activation energy is this? It's not very much, right? So with respect to getting these gigantic rate enhancements, we actually don't need to lower the activation energy all that much, right? This 30 to 90 kilojoules per mole is like a few hydrogen bonds, right? It's all we really need to offer our little transition state to lower the activation energy to get these gigantic rate enhancements, okay? So again, changes in activation energy, very small changes in activation energy will lead long-term to fairly large rate enhancements via our little equation here. Okay, so unfortunately this is going to have to continue. We're going to keep moving. This is transition state theory. Again, I'm going to go over how enzymes actually help in lowering the activation energy on Thursday. But now what we're going to move into is the best parts of this little lecture, which has just gone so well. We're going to go into deriving the Michaelis-Menten equation, which is how we model all of our enzyme kinetics. The reason I do this is because there are a couple of assumptions that we make in deriving this that you guys need to be aware of. Okay, so I don't just do this for fun. This is not fun for me at all. But again, you need to be aware of a couple of various assumptions that we make when we look at enzyme kinetics and how we model them. Okay? Okay, so we've gone over chemical kinetics. Enzyme kinetics is, again, just a branch of chemical kinetics. And so what we're going to imagine our little reactions as being is we have an enzyme and it has its substrate, okay? And we are going to model that enzyme binding to its substrate and producing products via a series of 3 separate steps, okay? In the first step, first elementary step, that's a big one, we're going to have enzyme come in and bind substrate, okay? Its product is going to be what we call the enzyme substrate complex, so ES together. That's our first step. And our second step, this little ES, second step, is going to convert to EP, which is the enzyme product complex. Okay, so this is our second step. It has its own little rate constant. And then in our third step, EP is going to essentially dissociate into enzyme and product. Okay, so this is a series of 3 separate steps. What are some of the intermediates in this reaction if we're looking at this as a mechanism? So one of the intermediates is ES, right? So again, this is it, and this is it. This is what we see overall in our overall reaction. What gets made and then immediately used? Enzyme substrate. What also gets made and immediately used? Enzyme product, right? So these two guys are intermediate species. There's a problem there. If we actually want to measure the rate of this reaction, can we measure intermediate species? No. So long term, part of this issue is that everything's going to be defined in terms of the enzyme substrate complex, but we can't actually measure that. So we have to manipulate things so that we can actually have things that we can measure moving forward in modeling our enzyme kinetics, okay? Okay, so 3 separate steps. This is an issue, right? 3 separate steps, elementary steps, is very difficult to deal with. So there's going to be one big assumption that we make very early on. Number 1, we're going to imagine that this reaction, ES going to EP, is essentially going to be our rate determining step, right? So this is going to be our RDS. It is also going to lie very, very, very far to the right, meaning it is going to be irreversible. Okay, so this is our rate determining step. It is also irreversible. Number two assumption that we're going to make, okay? We are only going to measure initial rates, okay? So initial rates of reaction. So in terms of product, what is that going to mean? If we essentially only look at the rate of the reaction at the very beginning, have we made any product? No, okay? So by only measuring initial rates, what we can assume about this last reaction is that it can't be reversible because we don't actually have any product built up for it to reverse in the other way, okay? So ES going to EP is rate determining, it's irreversible. We're not going to measure this for very long, so we're not going to have very much product built up. So this guy, long term, will break down into now a series of 2 separate steps where we have ES coming together to form our intermediate species, our enzyme substrate complex, and then this guy immediately breaking down to form product and enzyme, okay? These are going to have their own little rate constants. So this first reaction we are going to assume is reversible. So it's going to have a K1 forward, K minus 1 reverse, but then this second reaction again is rate determining, it's irreversible, so it only has a single-headed arrow, and we're going to call this K-cat, okay? So the rate constant for this second reaction is what we categorize as the overall rate constant for this reaction, okay? Why do you think we do that? This is our rate determining step, right? So in a mechanism, when we're looking at the overall rate of the reaction, who are we really watching? The rate of the rate determining step. Okay, so that's why we call this last rate constant K-cat, because this is the rate constant that we're looking at when we're actually measuring the rate of the reaction. Okay? Okay, so that's great. Now we have 2 separate steps. We can go about measuring how rate is affected by various different parameters. Okay, so again, we have our step number 1, our step number 2, and we have our K-cat here. All right, so if this is our rate determining step, our step number 2, what is going to be the rate law for this reaction? Since this is what we're watching, what is the rate law for this elementary step? So it's first order with respect to who? ES, right? So because of that, the rate for this reaction is going to be just the rate law of this second step, which is K-cat, the rate constant, times ES, first order, because again, it's an elementary step, and there's a 1 in front of it, okay? Now, this is it. This is the rate law for our overall reaction. There's a problem, though, right? If we want to actually measure this, can we measure ES? No, right? It's an intermediate, so we can't do anything with respect to this, right? What are things that we can measure? So we can measure We can measure rate. That's one thing we can measure, right? That's what we're essentially watching. What else can we control and measure? We can control substrate concentration, right? That's something that we can put in with our little pipette into our beaker. What else can we control? How much enzyme we put in. Okay, so these are the various things that we can control and that we can measure. Okay? So the goal of these next few slides is getting this ES in terms of something that we can actually measure. Okay? So just to note, the enzyme that we put in, and we'll come back to this in a second, this E total is going to come in two different forms. It's going to come in what we call free enzyme, as well as enzyme that's bound to substrate, so ES complex. These two things we can't know, but we can know the total amount that we put in. Okay, so one assumption, I'm going to actually just ignore this assumption. We're not going to talk about this assumption. So again, long term, what we're interested in is getting this in terms of the various things that we can measure: velocity, substrate concentration, and total enzyme, okay? One big assumption that we are going to make is what is called the steady state approximation, okay? So in the steady state approximation, this was given to us by these dudes named Briggs and Haldane. What we're going to look at is what happens to our enzyme substrate complex, which we're trying to get rid of long term, as this reaction progresses, right? So if we looked at these various concentrations as a function of time, and we looked at our little red line here, what happens initially when we start this reaction to our enzyme substrate concentration? It shoots up, right? But then after a certain point in time, what happens to it? Does it go down, or does it just stay constant, right? So it stays constant. So throughout the course of the reaction then, what is going to be the rate of change of enzyme substrate concentration over time? Right, so for this guy, this rate of change is equal to 0, as long as we move past that first initial jump, right? So this is what we call the steady state approximation. It's this idea that the concentration of enzyme substrate, after we move past that initial little jump, does not change throughout the course of the reaction, okay? Okay, so how does enzyme substrate actually change? What would be the various different reactions that would be leading to the rate of change of ES as a function of time? So if I write my two mechanistic steps, I have E plus S. This is reversible, making ES. And then I have ES breaking down into E plus P. Okay? So what different reactions are actually affecting the formation or the utilization of ES? So in the first reaction, what am I doing? Going forward in that first reaction, I am making ES, right? So we can write that as the rate law for that reaction, which would be given by this. So we are making ES. This is how the concentration is changing. What else is happening, though? The minute we make ES, we're also allowing in the fact that the reverse reaction can occur, right? So what would that do to the concentration of ES? It would decrease it, right? And so again, we can model that because this is an elementary step. So this would be changing the concentration of ES. This should be using it. Also, what's occurring on the second step? We're taking ES and we're making or using more of it. We're using more of it, right? And again, we can write the rate law for that. So this is using. Now, in the steady state approximation, once we move past the initial velocity, what is this rate of change of ES equal to? 0, okay? So we can go ahead and substitute that in. Oh God, I don't have time, I can't do this. So I'm gonna pause this right here, and I'm actually gonna finish this and get to the end on my own, and then we'll talk later about what happened. Okay, so I'm going to go ahead and pick up where I left off in lecture. So I'm going to try to go through the actual derivation here, so I don't have to bore you and take up time with the actual lecture time. So with the steady state assumption, the big idea is that after like the initial pre-steady state, the concentration of ES stops changing, right? So the change in concentration of ES as a function of time essentially equals 0. So we can go ahead and plug that in. And again, the concentration of ES is coming from a couple of different factors, or it's being affected by a couple of different factors. So in our first step of our Michaelis-Menten mechanism, we are making it. That is given or governed by this K1 rate law, as well as concentration of E and S. And then we are using it in the reverse, which is governed by this K inverse 1 or -1 rate law, concentration of ES. And we're also using it in the second reaction going forward. Okay, so that is governed by K cat, and then concentration of enzyme substrate complex. Okay, so I'm going to go ahead and plug in 0, because that is, again, is our steady state assumption for this guy. So then we are left with K1 times E, S, ES, and then I'm going to go ahead and rearrange this. Okay, so I'm going to rearrange. I'm going to move these guys both to the other side by adding them. And so I'm going to be left with K1 times concentration of enzyme, concentration of substrate is equal to K minus 1 concentration of enzyme substrate plus K cat concentration of enzyme substrate. Okay, and again, this big one is called the K cat, or the steady state assumption, pardon me. All right, so now we're going to take this guy moving forward. And again, the entire purpose of all of this is getting this intermediate species, this enzyme substrate complex, into some form that we can actually measure, right? So we talked about things that we can measure. Velocity was one, substrate concentration was another, and then total enzyme concentration was the last one. And so we're trying to rearrange our rate law to essentially get ES in some form of things that we can measure, okay? So we're going to start again with our steady state assumption. We are going to then factor out ES from our right-hand form of this equation, and then we're going to isolate it by dividing by the rate constants. Okay, so again, algebra occurs here. Algebra. Man, you think that I could spell. I can't, though, and that is apparent at this point in time. So algebra. Okay, so algebra occurs here, and this essentially turns into this guy. So now we have ES in terms of a couple of different things. Okay, so with this, we are going to define a parameter or a constant, and this is going to be called Km. This refers to the Michaelis constant, and we are going to define Km as this ratio of rate constants. And so this ratio of rate constants is essentially the inverse of what I have up here. So because of that, again, more algebra is going to occur. And this thing, when we plug in Km for this ratio of rate constants, is going to turn into this. Okay, so again, Km, this is ratio of rate constants. We call it the Michaelis constant. And we're going to talk more about what it means in a second. Okay, all right, so now we have ES. Right, so we've got our intermediate species in terms of substrate, in terms of a constant, and then we have it also in terms of enzyme. And right now this guy, this E is free enzyme, which is something that we can't necessarily know. Right, but what we can know and what we can control is total enzyme. So we mentioned this in the previous slide. Total enzyme was, again, the concentration of free enzyme as well as enzyme substrate. And so what we're going to do, because we know we can control total enzyme, is we are going to rearrange this to solve for free enzyme, and then we are going to plug that in to this guy up here. Okay, so when we do that, and then we factor in, because this enzyme is going to be equal to total enzyme minus enzyme substrate, and again, these are all in concentrations. When we actually plug that in and then factor the concentration of substrate into this guy, we are left with this thing right here, okay? So now we have ES in terms of Km, which is a constant, in terms of total enzyme, in terms of substrate, and then again, more ES and substrate. Okay, so then next, we're going to take that, we are going to rearrange, do some more algebra, and this thing, when we solve for ES, turns into this, okay? So now, we have enzyme substrate complex, concentration of it, in terms of E total, substrate, Km, which is a constant, and substrate. So these are all things that we can measure. And so that was the entire purpose of this entire activity, okay? Now we're going to take this, go back to our rate law for our rate determining step, and we're going to plug this thing in for ES, okay? And we get what is called the Michaelis-Menten equation, okay? So Michaelis-Menten equation gives us how our velocity, or our rate of this enzyme catalyzed reaction, is related to overall substrate concentration, as well as enzyme total concentration in these various parameters, Kcat and Km. And we're going to talk about these two constants, Kcat and Km, in a second. Okay, so now this is, again, the Michaelis-Menten equation, right? But this is not normally the way that you have seen it. So there's one little thing that we need to talk about before we can derive it to the point where you actually recognize it. So one thing to note, let's imagine that we have some sort of situation where the substrate concentration is much, much, much greater than the Km for the enzyme, okay? So if that's the case, then this term, this denominator term, if S is much larger than K, this essentially reduces down to just S, right? If that's the case, then S is going to cancel with S, and we are left with something that looks like this, where V is equal to Kcat times total enzyme concentration. Okay, and so again, this is way out here at very, very, very large substrate concentrations. And so in that point in time, essentially all of the enzyme is in the form of our ES complex, our enzyme substrate complex. And so essentially we have reached what we're going to call our maximum velocity, or our maximum rate of reaction. And so we're going to go ahead and we're going to substitute that in. So now we have V max is equal to this Kcat times this total enzyme concentration. And we will note that that Kcat times total enzyme concentration is in this equation. Okay, so we're going to go ahead and utilize now V max and substitute that in for that part of our little Michaelis-Menten equation, okay? So when we do that, we end up with this guy, which is velocity in terms of V max, which is going to be defined as the maximal velocity for our enzyme, again at this limit where substrate is much, much larger than Km, times substrate over Km plus substrate concentration, okay? We were in the process of deriving the Michaelis-Menten equation, right? And so it was this really long, boring mathematical thing. It was a bunch of algebra, okay? And so what I went ahead and did is I went ahead and finished that derivation, and I recorded it, okay? So when I upload this lecture, that derivation is going to be on that recording. I'm not going to finish it, though, because I'm promising you it's a bunch of algebra, a bunch of rearranging, and I've kind of given you all of the basic assumptions that go into our ability to derive the Michaelis-Menten equation. So at your leisure, please go back and watch the end of that derivation. But what we got to at the very end is given here. So this is the normal version of the Michaelis-Menten equation that you guys have probably seen before. Okay, so what this says is that the velocity or rate of our enzyme catalyzed reaction is equal to what we're going to call V max, and we're going to talk about what that is, times substrate concentration over Km plus substrate concentration. And so in that derivation, I think I talk about how we derive Km, etc. Okay, so From this, we have a rate, we have a substrate concentration, and then we have two other parameters, okay? So Vmax and Km. And so where Vmax comes from is this assumption that at really high substrate concentration, essentially all of the enzyme is in the form of enzyme substrate complex. So essentially, this rate reaction just breaks down into Kcat times total enzyme, okay? So Vmax is going to be what we define as the maximal velocity for our enzyme. And again, this is going to be at very, very, very large substrate concentrations, okay? Vmax is not a constant, though. We should note that. What is a constant is Kcat. This is going to be specific for the enzyme that we are dealing with. If we have Vmax and we know the total enzyme, then we can find Kcat, okay? But with respect to the Michaelis-Menten equation and the way we're going to move forward with it, we're going to have this in terms of Vmax. The other parameter that we come out of with respect to our enzyme kinetics is Km. So Km is called the Michaelis constant, and it is a ratio of rate constants. So the actual definition of Km is K minus 1 plus Kcat, and make sure these are tiny k's. So K minus 1 plus Kcat all over K1. Okay, and we'll go into what Km really means in the next slide. Okay, so two parameters, Michaelis constant and Kcat. And again, we have ended up with our beautiful little Michaelis-Menten equation, which relates enzyme velocity to substrate concentration, as well as these two enzyme parameters. All right, so now let's spend a second talking about how we can imagine these two parameters, Km, the Michaelis constant, as well as Kcat. So Km, let's talk now about these constants that we've introduced into our equation, right? So the first constant that we introduced was Km. Again, that's called the Michaelis constant. And I showed you what it was. It was that ratio of rate constants, but that may not make too much sense just looking at it, right? So operationally, we can define kind of a working meaning of Km, right? So let's imagine that Km is equal to substrate concentration. So if we write down our Michaelis-Menten equation, we have velocity is equal to Vmax times substrate all over Km plus substrate, okay? And so in this little scenario, we're going to let Km be equal to substrate concentration. So when that happens, we have velocity is equal to Vmax times substrate over substrate plus substrate. So that's going to give us two S's on the bottom. And so what this essentially reduces down to is velocity is equal to Vmax over 2. Okay? And so this is going to be kind of our working operational meaning of what Km is. It is essentially going to be the concentration of substrate that gives us our half maximal velocity. Okay, so that again is our operational meaning, our working meaning of Km. It's going to be the substrate concentration at half maximal velocity, but we can also define kind of a more conceptual meaning for what Km is trying to illustrate. So we had defined the Km as being that ratio of rate constants. So this was K minus 1 plus Kcat over K1. Okay, and so that K1 and K minus 1, those are the rate constants for that original first step in our Michaelis-Menten mechanism, right? So in that first step, we had E combining with S, forming ES. And so the forward reaction was represented by the rate constant K1, and the reverse reaction was represented by the rate constant K minus 1. Okay, so we're going to imagine a situation where Kcat, so Kcat is much, much, much less than K minus 1. Okay, so in that scenario, if Kcat is very, very, very small, and K minus 1 is very, very, very large, then this essentially reduces down to this K minus 1 over K1. Okay, so again, we haven't really talked necessarily about this, but this is the equilibrium constant, or the ratio of rate constants for the dissociation of enzyme substrate complex to E and S, right? So this is essentially a dissociation constant. And we can kind of think of Km in a similar term of this dissociation constant. So kind of in another type of meaning with respect to this is the smaller the Km, so smaller Km, the more affinity our enzyme is going to have for substrate. Right, because the smaller the Km, the less, if we're thinking in terms of a dissociation, right, so if we're dissociating, the smaller the Km, the less there are of these guys at equilibrium, and so the more we have in the form of this enzyme substrate complex. So this gives us a good idea of the overall affinity that our enzyme has for substrate. If we want some sort of nice, easy working definition, okay, if we go back to our little Michaelis-Menten equation, and we are at a substrate concentration that is equal to Km, this Michaelis constant, we can go ahead and plug that in. So we get V is equal to V max times substrate. And again, we're assuming this situation where Km is equal to substrate concentration. So that would mean substrate plus substrate. And S plus an S, what does that reduce down to? 2S on the bottom. So if we have 2S on the bottom, it's going to cancel with our S up top. And we are going to be left with V is equal to 1/2 V max. Okay? So that is a nice, easy working definition for what we can imagine this Michaelis constant to be. This is going to be the substrate concentration where our velocity is 1/2 the maximal velocity, 1/2 V max, okay? Okay, so Km has a different meaning as well, though. And we can kind of go back or derive this different meaning in terms of what the original definition of Km was. So Km, when we originally defined it, was equal to K minus 1 plus K cat all over K1. And what were these K1s, these K minus 1s? What did they refer to? If we go back to our original mechanism, so the K1 was the rate constant for the association of enzyme and substrate. Again, let me make this clear. So K1 was the forward rate constant for this reaction, whereas K minus 1 was the reverse rate constant for the backward reaction, where we're having enzyme substrate dissociate into enzyme plus substrate, okay? So now, if we assume, which is kind of a good assumption to make sometimes, that K cat is much, much less than K minus 1, then what is this reduced down to? If K cat's really tiny and K minus 1 is really big comparatively, what is this definition of Km reduced down to? So this ends up just being K minus 1 over K1, which is defined as the dissociation constant for enzyme substrate complex, okay? So this ratio of rate constants is the equilibrium constant that essentially tells us about this dissociation of enzyme substrate into enzyme plus substrate. Okay, so again, this is a dissociation constant. So the smaller the value of Ks, this dissociation constant, and correspondingly Km, because this is what we're kind of imagining Km to be, the smaller this value, the more of these guys exist at equilibrium, right? So we can utilize this definition as another overarching idea behind Km. This can be essentially a measure of the affinity of enzyme for substrate, okay? So for the smaller value of Km, the greater the affinity of enzyme for substrate. Okay? Smaller value of this association means that they come together and they like to be together. Okay? So that's another working definition that we can have for Km, a measure of the affinity of enzyme for substrate. The smaller the value, the more affinity there is. Okay? All right, so that's Km, working definition. Substrate concentration at half maximal velocity, also a good measure of overall affinity of enzyme for substrate. Now the other constant that we had was Kcat, right? So Kcat. Okay, so what about this other little catalytic parameter or enzyme parameter that came out of the Michaelis-Menten equation? So now we're going to talk about this guy, this little Kcat, right? And again, Kcat is a rate constant, and it was the rate constant. It was the rate constant for our rate limiting step, right? So Kcat is essentially the rate constant for the overall reaction. And we frequently will call this the turnover number, right? Because what it's going to do is it's going to essentially tell us the number of molecules that react per unit time. So Kcat has units of inverse seconds, right? And so, for example, if we had a Kcat of 10 per second, that would tell you that the enzyme turns over 10 times per second, right? So it's giving you an overall idea of the rate of the reaction. So the larger the Kcat, the more turnovers we get per unit time, the overall faster rate of the enzyme. Okay, so also Kcat is related to total enzyme. So we had derived that relationship where Vmax was equal to Kcat times total enzyme concentration. And so with the Michaelis-Menten equation, the way we usually write it is we usually write it in terms of determining Vmax and then determining Km. And again, we'll talk about how you guys are going to determine that in a second. But we don't really talk about how you get Kcat. Well, the big idea behind this is that if you can determine Vmax and you know total enzyme, which you should know this, then you could determine Kcat from that. So how do you get Kcat? Well, you need Vmax and you need total enzyme. Okay, so one other little thing, there is going to be kind of a particular relationship between Kcat and Km. All right, so if you think about an enzyme, the larger the Kcat, the more molecules are going to react per unit time, right? So the faster the enzyme. Also, the smaller the Km, the more affinity the enzyme has for substrate, okay? So high affinity and a very fast rate constant is going to lead to a very large ratio of this Kcat to Km. All right, so we're going to be able to utilize this ratio as kind of like a measure of overall enzyme efficiency and specificity. Okay, so this Kcat to Km ratio, the larger this is, the more efficient and more specific the enzyme is for substrate, okay? All right, so where does that kind of derive from? Why would we take this ratio of Kcat to Km? So we can imagine, so let's assume that we have some sort of situation where we have very low substrate concentration, right? So substrate is super low, and it's going to be very, very, very low comparatively to the overall value for Km. Okay, so in that type of limit where we have very low substrate concentration, then we can also assume that all of the enzymes, so total enzyme concentration, is in the form of free enzyme because there's not enough substrate essentially around to bind to our enzyme. So all of the enzyme is going to be free. So in this limit of very low substrate concentration, the Michaelis-Menten equation essentially reduces down to this, right? So velocity is equal to this ratio of Kcat to Km times enzyme times substrate, right? And so what we can look at this as as this second order reaction between enzyme and substrate, and in that case, this becomes this second order rate constant. And it has units of inverse molar, inverse second. The higher this value is, the higher this ratio is, the faster this overall reaction, so the faster this overall enzyme, okay? All right, so this ratio is going to have a limit, all right? And so the limit is essentially what we call the diffusion controlled limit, right? So this limit is going to have a value of about 10 to the 8th to 10 to the minus, or 10 to the 9th inverse molar, inverse second. So this is the maximum possible value that this ratio of kcat to Km can obtain. And again, this is what we call diffusion control. So literally, what we are looking at, if we have an enzyme that has a kcat to Km ratio of 10 to the 8th to 10 to the 9th, is that every time a substrate diffuses into the enzyme, it turns over immediately, right? We are literally waiting on substrate molecules to diffuse to the enzyme. And this is the rate at which molecules can diffuse in basic biological type system, okay? Okay, so again, this ratio, it's going to give us the overall efficiency of an enzyme. It's going to have a maximum possible value, and that's essentially going to be this diffusion controlled limit, wherein we are essentially just waiting for diffusion to bring us a substrate. The minute it does, it immediately turns over. It was related to Vmax. So kcat was related to Vmax. Vmax was defined as kcat times total enzyme. Vmax is what appears in the Michaelis-Menten equation, but Vmax, again, is not a constant, right? It depends on total enzyme concentration. Kcat, though, on the other hand, is a constant. It is specific for the enzyme, just like Km is specific for the enzyme. So we utilize kcat as opposed to this Vmax because, again, it is actually specific for the enzyme. So how can we imagine kcat? So if we go back to what kcat is, it was the rate constant. That was the rate limiting step in our enzyme reaction, right? It had enzyme substrate breaking down into enzyme end product. And again, this was the rate limiting step. So essentially what this is the rate constant for our overall reaction. If we have lots and lots and lots of substrate present, and so all of our enzyme is in the form of enzyme substrate, what we are watching is this rate constant as we actually watch our enzyme catalyzed reaction, okay? Okay, so kcat, if we look at this is again the rate law. Is this a unimolecular or a bimolecular reaction? Unimolecular, right? So what units would kcat have? One, so it depends on one. So kcat's going to have units of inverse seconds, okay? And so we can utilize that to kind of imagine what kcat is telling us. It's what we call the turnover number. If we had a kcat that was equal to 10 inverse seconds, what that's telling you is that the enzyme turns over 10 times per second, right? It's just the turnover number. It's essentially going to be how many times enzyme turns over per unit time. Okay, so the larger the kcat, what do you think you can say about the enzyme? The better the cat is. The larger kcat, the more it turns over per unit time, the faster the overall rate of the reaction, the faster the catalyst, okay? Okay, so there's one more little thing that we're going to get from our two different constants here, Km and kcat. And so this, again, is going to come in one of these abstract ideas. So we're going to assume that we have very little substrate. So we're going to assume that we're in a situation where substrate is very much limiting. It is much, much, much less than the value for Km for the enzyme, okay? In this case, what that essentially implies is that total enzyme is essentially going to be equal to free enzyme, right? If there isn't very much substrate, then not very much enzyme substrate complex is actually going to have formed. So pretty much all of the enzyme is in the form of free enzyme. Okay, so in that case, what the Michaelis-Menten equation breaks down into is given here. Okay, so Michaelis-Menten, essentially in this limit where we have very little substrate, and so all of the enzyme is free enzyme, Michaelis-Menten turns into this equation, okay, where velocity essentially becomes a bimolecular reaction, right? It depends on the concentration of enzyme and the concentration of substrate. Okay, so in this case, all we are waiting for is enzyme to find substrate, and now in that case, what we have is this ratio of Kcat over Km. This is going to be what we define as this second order rate constant for this bimolecular reaction. So second order rate constants, what are the units that they have? Right, so m minus 1 over s minus 1. Okay, so this guy again is going to be the second order rate constant, and it's going to have units of inverse molar, inverse seconds. Okay, now what is this little rate constant going to tell us about the overall efficiency of this reaction? Because this is what we're going to utilize this ratio for. It's going to tell us about the efficiency of our enzyme catalyzing this reaction. Okay, so what do you think a large value of this is going to do overall to the velocity of the reaction? So large rate constants, what do they do to affect the overall velocity or rate of the reaction? It's going to be a faster rate of reaction, right? So the larger the rate constant here, the faster this enzyme is going to be able to catalyze this reaction, okay? What's going to give us a large value? So we have this ratio of Kcat over Km, then Kcat, if Kcat is large, that's going to give us a large rate constant, or this large ratio at least. What about Km? If we want to make sure that this is as large as possible, so this is the most efficient enzyme as possible, what does Km probably need to be? Small, right? So a small value of Km, a large value of Kcat for the enzyme is going to lead to a very large ratio of this Kcat over Km, which is again how we measure the efficiency of our enzyme. So that means that we have a high turnover number. So a high turnover number, and again, what is Km, a small Km, what does that tell you about the affinity for enzyme and substrate? So a small value of Km means large affinity. So large affinity of enzyme for substrate. Okay, so again, the larger this ratio, the more efficient, the better our enzyme is at catalyzing its reaction. So now there's going to be a limit to how far this ratio can go, okay? So this ratio is going to approach what we call a maximum limit. And it's essentially going to be 10 to the 8th to 10 to the 9th inverse molar, inverse second. So if you had an enzyme and it had this Kcat over Km ratio of 10 to the 8th-ish, essentially what that's telling you is that this enzyme is so efficient that the minute a substrate molecule diffuses to it, it turns over, right? Because this is essentially the rate of diffusion in biological systems. Okay, so if you do have an enzyme and its ratio of Kcat over Km is approaching what we call the diffusion limit, then it has reached what we call catalytic perfection. Okay, because again, what it's telling you is that the minute a substrate diffuses to the active site, the enzyme turns over immediately. Okay, so again, if we do have enzymes that have reached this limit, they have reached catalytic perfection. They are a catalytically perfect enzyme. Why would you think that be? Why has it reached perfection when it reaches this ratio? So can diffusion happen any faster? No, right? And so there's no essentially pressure past this point, because diffusion cannot occur any faster, by which it would evolve to be any better at what it's doing, right? So it has reached this point where the minute a substrate diffuses to the active site, it turns over. Diffusion is not going to happen any faster, so this is what we determine as catalytic perfection with respect to enzymes. And there are a few enzymes that actually have reached this Kcat to Km ratio that approaches what we call the diffusion limit. Okay, so Km, measure of enzyme affinity for substrate. We have Kcat, which is the turnover number for our enzyme. And then this ratio is another way to judge how good our enzyme is at catalyzing its reaction. So now we're going to go into how we actually determine these values for Km and Kcat. All right, so we have done this in the lab. All right, so we determined the Km for LDH with respect to, what do we do it for, NAD? Something like that? So you guys did that, okay? We also determined Vmax. So we're not necessarily interested, again, in Vmax, but Vmax is how we're going to essentially determine what Kcat is. All right, so how do we actually experimentally go in and do this? So number one, we run multiple reactions. And in those multiple reactions, what we do is we measure the initial rate of the reaction as we vary initial substrate concentration. Okay, so we will vary the initial substrate concentration that we put in, and we will measure the initial rate of each reaction. With those values, we will go in and we will make what we call this Michaelis-Menten plot, where we plot initial velocities as a function of initial substrate concentrations. We will get something ideally that looks nice and hyperbolic if it follows Michaelis-Menten kinetics, because again, the Michaelis-Menten equation, what is its form? Vmax substrate over Km plus substrate. This essentially forms a hyperbola, right? This is the equation of a hyperbolic line. So this is how we would get our nice little Michaelis-Menten kinetics graph. All right, so now how would we determine the Km and then the Vmax from a graph like this? So what is Vmax? Vmax is maximal velocity, right? And so we'll note that our little hyperbola reaches a point, right, and it's going to continue to go on. So how do we estimate Vmax? It's essentially where this velocity is going as we move to infinite substrate concentrations. So it's essentially going to be this asymptote to this hyperbolic line. Okay, so that's how you would estimate Vmax if you were given a Michaelis-Menten plot. So what would you say Vmax is here? Probably about 150. So then how would you get Km if we were just estimating eyeballing this, right? So you would go, again, Km is substrate concentration at half maximal velocity. What is half of 150? About 75. You would go over to the curve. The substrate concentration at that point in time is what we define as Km. What are going to be the units here of Km? What are units of substrate? Molar. Okay, even though it's supposed to be this ratio of rate constants, kind of like an equilibrium constant, Km is going to have units of molarity. All right, so that is how you guys determine what Km and Vmax is. Oh, well, okay, so that's Vmax, that's Km. What about Kcat? What else do we need? Because again, we don't care about Vmax long term. How would we get Kcat if we knew Vmax? We would also be having to be given the total enzyme concentration, which is again something that we can control. Okay, so you would estimate Vmax from the plot, and you would get Kcat if you knew the total enzyme concentration. Okay, so that's how you guys would do it if you were taking an exam or you're in the lab, something like that. How do real people do it? How do real scientists actually determine these values of Km and Kcat? So they do science, right? So they measure, again, initial velocities as a function of substrate concentration. They make these beautiful little Michaelis-Menten plots, and then what they do is they utilize nonlinear fitting programs to essentially determine the optimum values of Vmax and Km. So they will take their data in the Michaelis-Menten equation, the Michaelis-Menten form, and they will fit this hyperbola and optimize these values to determine their actual values. Okay? That's how scientists really do it. We don't actually utilize what I'm going to show you next, which is the linear linear regression of whatever happens to this Michaelis-Menten equation, okay? So reality, we actually use these fitting programs to determine these values. What if you're in an exam or you're in something where you can't actually use any type of fitting program to figure this out? Would be another way, besides estimation, which is what we just did, to determine the Km and Kcat. So we're going to take our little equation and we're going to transform it into a different version, right? So the version that we tend to like to show you guys is the Lineweaver-Burke plot. So this is what we call the double reciprocal plot, okay? It is going to take our Michaelis-Menten equation and it is going to take the reciprocal of both velocity as well as substrate concentration. When we do that, we get a nice little linear format. So in the Lineweaver-Burke plot, we're going to plot 1 over velocity on the y-axis and 1 over substrate concentration on the x. So this is going to take this nice little y equals mx plus b. The y-intercept ends up being 1 over v max. So again, if you've used some sort of linear regression, you could fit this line, get the y-intercept, and determine v max from that. The slope is equal to km over v max. Okay, so this is one way that we're going to look at this, and we're going to continue on with the Lineweaver-Burke plot, even though it does not utilize all that frequently, because it's going to allow us to easily determine, when we're looking at inhibition, the types of inhibition that we're actually seeing. And we'll show you that in a second when we talk about various types of inhibitors. Okay, so let's go ahead and try a question that utilizes this. It's nice and easy. I have a Michaelis-Menten plot, and I want to know which number best estimates the Vmax for this reaction, for this enzyme. Go ahead and get your answers in if you haven't yet. All right, so what is the best estimate, or which point represents the best value for Vmax? So A, right? So A would be the correct answer here. What about this one? Okay, so again, get your answers in if you haven't yet. All right, so Km, what is Km operationally defined as? Substrate concentration at half maximal velocity. If A was Vmax, then B is a good estimate of 1/2 Vmax. And so then what refers to Km? C, right? So the substrate concentration at half maximal velocity, the correct answer was C. And those are nice and easy. Easily circle in your answer, or do whatever you are on the Scantron. Something like this would be a little bit harder. Right? So I have a nice little Lineweaver-Burke plot for an enzyme catalyzing its reaction. And in this one, I want you to tell me what the kcat of this reaction is, given that I've told you total enzyme concentration. Giving the equation for the line, giving you total enzyme concentration. Again, this is 1 over V and 1 over S. Yep. Three is fine. It doesn't have the correct answer, but it doesn't have a correct answer, so whatever you put in. Satisfactory.
Do we just use the relation with that? Does that work?
Yeah, that'd be fine. Take a few more minutes if you haven't gotten your answer in. A few more seconds, 30 seconds. Okay, so there wasn't a correct answer in Socrative, but most of you didn't quite get it. It's all right, it's all right. You have it in your own mind. That's the only thing that matters. So the only thing to note here, I think most of you went about this the right way. With the Lineweaver-Burke plot, the y-intercept is equal to 1 over V max. I give you the equation for this line, right? And I give you the y-intercept. So 0.83 is equal to 1 over V max. And so then V max is just the inverse of 0.83. That gives us a V max equal to 1.2. But what's important to note here is units. All right, so the units for our 1 over V's were inverse micromolar seconds, right? So the units for our V max is micromolar inverse seconds, right? That's just a rate. A velocity is going to be used in molar or micromolar per second. Okay, so that's micromolar. To get k cat, we have V max is equal to k cat times total enzyme concentration, and total enzyme concentration is given to us in units of millimolar. Okay, so what I'm going to do, just to kind of keep this easy, is I'm going to substitute the prefix multipliers by what they're supposed to be multiplying by. So micromolar is 10 to the minus 6 molar per second is equal to k cat, and then millimolar is 10 to the minus 3. So I'm going to go ahead and substitute that in to quickly convert to molar. Okay, so when you solve for k cat, what is that? 0.120, and what are going to be the units here if the molars cancel? Inverse seconds, which is usually what k-cats are written in terms of, right? So k-cat is an inverse second. So a lot of people got 120, which would have been what you would have gotten if you hadn't converted the millimolar, right? Maybe something like that. Or did I do math wrong? That's my question right now. Usually when people get different answers and I get something entirely different, I worry that I did math wrong. But if you take this and you divide it by that, that is 0.12, right? Okay, all right, good. All right. One more. So that's KCAT. That's how you would get KCAT if I gave you some sort of nice Lineweaver-Burke plot. So similar type thing. I want to know what the Km for this exact same reaction is. All right, so get your answers in if you haven't yet. Okay. Okay, so most of you guys, I think, got this correctly. So, again, with the Lineweaver-Burke plot, the slope of the line is equal to Km over Vmax. We had Vmax from our original problem. Vmax we already solved for was 1.2 micromolar inverse seconds. And then we have a value for slope that's 0.21 is equal to Km over Vmax. Because the slope and the Vmax have the same exact units at this point in time, when we leave this in terms of micromolar, we don't have to do any type of conversion here. So all I'm going to do is multiply my Vmax by my slope, and my Km ends up being 0.253. If we want to keep 3 sig figs, I don't care. What are the units, though? So this is going to be units of micromolar. Okay, so that's actually a fairly tiny Km, even though it looks, it's almost like a whole number integer value. Make sure to note that the units are very small. So this is actually a very small Km. Okay, so moving on, we have a few more things to talk about. The next thing we're going to go into is inhibition, so enzyme inhibition. All right, so inhibitors essentially affect the overall enzyme by decreasing its activity. Okay, there are a lot of different types of inhibitors, and the reason why we're interested in enzyme inhibition is, first off, they actually give very good information with respect to the overall mechanism of our various enzymes. But second, how are inhibitors utilized a lot of times in modern biomedical sciences or something like that, right? So inhibitors actually form the basis of a lot of the various drugs that we put out onto the market. They are actually inhibitors of various enzymes, and so that's why inhibition and our various types of inhibitions are actually kind of important in understanding. So we're going to talk about 3 different types of inhibitors. We're going to talk about competitive inhibitors, uncompetitive, and then a third type, which is what we're going to call mixed inhibition, mixed inhibitors. They're all going to have a different type of effect on our overall enzyme catalyzed reaction. We're going to talk about how each one actually affects it. We're going to start with competitive inhibition. Okay, so in competitive inhibition, we are going to have an inhibitor. So that inhibitor is going to come in, and it is going to be attracted to the free enzyme. It is actually going to bind at the active site of the enzyme. Okay, so in competitive inhibition, the inhibitor binds to the active site of the enzyme, which makes substrate binding impossible. Okay, it is going to bind, and it's going to bind in what we're going to call a reversible manner. Okay, so it binds, but it can also come off. This is not an irreversible type of reaction. So when the inhibitor, and this competitive inhibitor, binds, it's going to take up space on these enzyme active sites, but it's not going to turn over and do anything, right? If it actually turned over and made a product, then it would just be essentially a competing substrate. Instead, it's just going to block the active site from the actual substrate that we want. Okay, so in this competitive inhibition, when the inhibitor is attracted to the active site of the enzyme, how is that going to affect our Michaelis-Menten kinetics? My bad. Okay. I don't know why it skipped like that. Okay, so again, in the presence of a competitive inhibitor, because the enzymes are taken up by the presence of that inhibitor, substrate's not going to have as great of effect as it would in the absence of the inhibitor. Okay, so long term, the way that's going to affect our Michaelis-Menten kinetic plot is we're going to see an increase in the Km of the enzyme in the presence of this inhibitor compared to the absence of the inhibitor. Okay, so again, because it takes up spots on the enzyme, substrate can't get in. At equal substrate concentrations, we're not going to get as quick of a reaction, and that's going to have an effect of essentially increasing the Km for the enzyme. So in competitive inhibition, the Km is always going to be larger in the presence of the inhibitor than in the absence of it. Okay? What about Vmax? So in competitive inhibition, again, this inhibitor is binding to the enzyme, but this is in a reversible fashion, right? So if we flood the system with substrate, long-term the substrate is going to outcompete the inhibitor, right? So at infinite substrate concentrations, we're still going to get to the exact same Vmax, okay? So in competitive inhibition, we see an increase in Km, and we call this Km apparent, because again, it's the apparent Km, but we're not going to see any effect, so no effect, on the actual Vmax. Okay, so when we plot these guys in the Michaelis-Menten equation, or Michaelis-Menten plots, it's kind of hard to see the fact that this is a competitive inhibitor, right? But if we have a different Km, so a larger Km, but we have the exact same, we have the exact same Vmax, if we plotted this in Lineweaver-Burke, what would the Lineweaver-Burke plots for these guys be in both the presence and the absence of the inhibitor? Right? What would they have the exact same? If we think about Lineweaver-Burke and our various things, they have the exact same y-intercept, right? So what we see in competitive inhibition is essentially if we were actually to plot on our Michaelis-Menten plot, something has happened. I think I lost the slide somewhere. There. Inhibition makes itself very well known if you were to take the Lineweaver-Burke plot in the presence and the absence of the inhibitor, right? So in the presence of the inhibitor, we would have our nice little normal Lineweaver-Burke plot, or in the absence of inhibitor, pardon me. In the presence of inhibitor, because we have this larger Km, we're going to get a larger slope. So in the presence of inhibitor, we are going to get a steeper Lineweaver-Burke plot, but comparatively, they're both going to come back to the exact same Vmax, so they're both going to have the same exact y-intercept, okay? So presence of inhibitor, we're going to get a steeper slope, but we're going to have the exact same Vmax regardless. Okay, so that is competitive inhibition, and again, it kind of manifests itself. So this is presence of inhibitor, and this is absence. We're going to see that in the Lineweaver-Burke because both of these guys are going to come to the exact same y-intercept. And again, what is competitive inhibitors? What do they do? Where do they bind? At the active site. So they are competing with the substrate for binding in the active site. Okay, so a second type of inhibition is called uncompetitive inhibition. Okay? In uncompetitive inhibition, we're going to have our inhibitor, and instead of binding free enzyme, it's going to bind specifically to the enzyme substrate complex, okay? So in uncompetitive inhibition, we get binding exclusively to enzyme substrate complex. Since that is the case, can the competitive inhibitor bind at the active site? No, right? So can the uncompetitive inhibitor bind at the active site? So no, because again, substrate is already bound. So in uncompetitive inhibition, we're usually going to get binding at some sort of secondary site away from the active site. That binding at that secondary site is going to do some sort of conformational effect to the protein so that it actually can't catalyze its reaction, and so we don't get catalysis in this uncompetitive inhibition. Again, this is also reversible. Okay, so how does uncompetitive inhibition kind of manifest itself or display itself with respect to our enzyme kinetics? So what we're going to see in uncompetitive inhibition is the Michaelis-Menten equation is going to turn into a Vmax apparent that is essentially decreased by this factor alpha. And we're going to get our Km apparent, which is also decreased by the exact same factor alpha. So in uncompetitive inhibition, we're going to see both a decrease in our Vmax, and we're also going to see a decrease in our Km. But that decrease is going to be the same for both of them. It's going to be decreased by this exact same factor alpha prime, okay? So as we look at this in the Lineweaver-Burke plot, if we get a decrease in Vmax, how is that going to manifest itself when we plot these in a linear format? What's going to happen to the y-intercept if we get a decrease in Vmax comparatively? We're going to get an increase in the y-intercept, okay? So if we have no inhibitor versus inhibitor in uncompetitive inhibition, what we're going to see is this increase in our y-intercept in a Lineweaver-Burke plot. We're also going to see an increase in Km, but what's important with respect to this guy, what was the slope in the Lineweaver-Burke plot again? So slope was Km over Vmax. Because both Km and Vmax have been decreased by this alpha, the same exact alpha, when we take the ratio, the alpha is going to factor out. So long term, what we see is the exact same slope in no inhibitor versus the presence of inhibitor. Okay, so we see this increase in Vmax or increase in y-intercept, but we have the exact same slope regardless, because again, the ratio of Km over Vmax is going to be the same. The alphas essentially are going to cancel. Okay, so then last one, this is uncompetitive. You're going to see this decrease in Vmax, decrease in Km. You're going to get these parallel lines when you plot the Lineweaver-Burke plots in the absence versus the presence of inhibitor. The last type of inhibition is what we're going to call mixed inhibition. So competitive inhibitors bound to the active site, they outcompeted the substrate at the active site. Uncompetitive inhibitors bound to some other secondary site, they didn't bind to the active site. So in mixed inhibition, what's going to happen is we're going to have an inhibitor that has affinity for both the active site, like in competitive inhibition, as well as a secondary site away from the active site, like in uncompetitive inhibition. So we call this mixed because essentially the inhibitor displays a mixture of both types of inhibition. Okay, so there's going to be a special case, and I'm just going to mention this briefly. Right, we have defined essentially these little equilibrium constants as this dissociation constant of both free enzyme and inhibitor, as well as enzyme substrate complex and inhibitor. The special case where this Ki is equal to Ki prime, this is the particular case which is called non-competitive. Non-competitive inhibition, this frequently does not happen though, so it's technically called non-competitive inhibition. In reality, though, these guys are different from one another. The inhibitor displays different affinities for the enzyme versus the enzyme substrate complex, and so we actually don't see this pure non-competitive inhibition. Okay, so how is this going to manifest itself? How is this mixed inhibition going to affect our Lineweaver-Burke plots as well as our Michaelis-Menten kinetics? Okay, so what's going to happen is our apparent Vmax, so the Vmax in the presence of inhibitor is essentially going to be reduced by some sort of factor alpha. So we're going to see a decrease in Vmax. Where else did we see this? What type of inhibition? Who decreased Vmax? So uncompetitive inhibitors, we saw a decrease in Vmax. But on the other hand, Km, the Km apparent in the presence of inhibitor, is going to actually be increased by a factor of alpha over alpha prime. So alpha tends to be a little bit larger than alpha prime. So because of that, we will see an increase in Km. What type of inhibitor do we display an increase in Km? Competitive inhibition, right? So this is what we mean by this mixed inhibition. We see principles of uncompetitive inhibition, and we also see principles of competitive inhibition. So what that's going to manifest itself like in our little Lineweaver-Burke plots is we're going to see a change in the y-intercept, and we're also going to see a change in the slope. Okay, so these lines are not going to be perfectly parallel, as you would see in uncompetitive inhibition. They're not going to come back to the same y-intercept. Instead, they're going to meet at some point that's off to the side that has no meaning with us for the most part. Okay, so mixed inhibition, you're not going to get parallel lines. You're not going to get the same y-intercept. Okay, and that's because, again, we see this decrease in Vmax. We see this increase in Km. Okay, so just utilizing that, making sure it's mentally present, let's go ahead and take one little question, something that you could possibly see on an exam. So I have a Lineweaver-Burke plot of an enzyme in the absence and then in the presence of increasing inhibitor. I want to know what type of inhibitor is this? Oh, yeah. Okay, so this one's kind of easy. I don't even ask about what type of inhibitor it is. So we haven't talked about what positive modulators are really. What is the correct answer here? It's B. What type of inhibition is this? Competitive inhibition, right? We have the inhibitor coming in and binding to the actual active site of the enzyme, taking that spot away from the substrate. Again, we know that because these guys all come back to the same y-intercept. All right, so I actually inserted different slides that I wanted to talk about. I'm not going to talk about them, though, because I just can't at this point. There's also a part at the end that talks about bi-substrate reactions. I am also not going to cover bi-substrate reactions. But the whole idea behind Michaelis-Menten, we only had one substrate binding, right? But a lot of enzymes actually have two substrates binding. What type of enzymes or what class of enzymes would you expect two different things to need to bind to the active site to actually get catalysis? So oxidoreductases is one. A lot of times we'll have some sort of redox active cofactor that must bind. What about another one? So transferases, ligases, when we need to ligate two things. Transferases, what do? Transfer a functional group. That functional group usually needs to come from somewhere. Okay, so that's another class. I'm not going to go into bi-substrate reactions, though, but just note that Michaelis-Menten kinetics does not cover all types of enzymes because, again, we're only assuming one substrate. Okay, so that's all I have to say.